Hello everyone, my name is Qian Zhang. I'm a PhD student in Southeast University. And today I want to talk about our research on programmable and reconfigurable surface with Kirigami-inspired BISTABLE elements, co-authored by myself, Ms. Pan, Professor Tai, and Feng. Let's go straight to the topic. It's very important to provide a powerful strategy to transform 2D element to 3D complex surface with different scales. For the larger scale structure, elastic grid shells are designed to erect the covered geometry by the active bending strategy. Besides, bending planned structures, textile hybrids, and elastic kinetic structures have also been exploited to achieve 3D efficient architectures. For the smaller scale structures, there are three main ways to achieve reconfigurable surface. The first one is to combine electric, magnetic, thermal, or other actuation wells with mechanical properties of the material and structures. In Figure A, an electric field is formed between the two set surfaces to produce an out-of-plane driving force. Besides, we can take advantage of the mechanical instability to achieve geometry transformation of the structures. In Figure B, the out-of-plane deformation will emerge due to the in-plane tension on the film with pre-designed cuts. Apart from that, the pre-stressed substrate in Figure C can guide and control the compressive buckling behavior of the film with predefined creases to form the target 3D configuration. From the perspective of the manufacturing technology, the latter methods are more attractive and convenient. However, the out-of-plane shape is always sensitive to the in-plane load state. When the external loads are removed, the structure will also return to the initial flat state. Now we want to explore a novel path to achieve stable reconfigurable surface by active shaping and recovery. We want to introduce the Kirigami-inspired rotational erection system. The pattern has been explored in the application in the haptic swatch. The solid black lines, the red dotted lines, and the solid red lines represent the creases, cuts, and constraints, respectively. This pattern can be determined by 5 parameters: side length of the outer square edge A, side length of the inner square facet B, the rotation angle of the inner square relative to the outer square theta, the in-plane relative offset of the vertex dx and dy. In the simulation analysis, the fixed lines are constrained with all translational degrees of the freedom. When the model is subject to vertical displacement loss u on the central square facet, the strain energy and rotational displacement of the central square facet phi are used to represent the configuration of the folding and unfolding process. In this figure, the red line represents the strain energy, and the blue line represents the rotational angle. In the tension process, the strain energy goes up with the upward vertical displacement. After skipping over the valley, the model starts to rotate clockwise. In the state T5, at the maximum tension displacement of the 20 mm with maximum strain energy, the model is unstable. It's worth noting that the model will move to another BISTABLE state, C1, rather than back to its initial state, T1, when the external loads are removed. We also performed the compressive analysis of the Kirigami-inspired model from the state C1. The rotational displacement always increased, but slightly, and the model will not move along the tension path. The strain energy climbs all the time. The state C4 is unstable, and the model will move back to state 1 once the external compressive displacement loads are removed. There is the self-locking phenomenon. We want to try the analysis of the in-plane tension. There is a circular base for the Kirigami-inspired element. The in-plane tension concentrated displacement loads are applied at the edge of the circular, with the direction parallel to the diagonal line of the outer square, and the constraints of the fixed line are removed. We can obtain the relationship between the actuating displacement and the corresponding force. The force firstly increased and reached a peak, followed by a decrease, and then the actuating force shoots up back to around the peak during a short actuating range. In this process, the configuration is close to the folded stable state. Subsequently, we remove the actuating displacement rows, and the displacement of the actuating poles decrease gradually. The Kirigami-inspired model of the stable state S9 has a slight shrink along the loading direction in contrast to the initial flatter state. After finding the shape results, we also conducted the parametric analysis to investigate the influence of the actuating position. We define the load angle lambda by rotating the diagonal direction of the outer square to the actuating direction. Firstly, it needs to be clear that the shaping will fail when the loading angle is not less than 30. When the loading angle is smaller than 30, the other folding stable state will be obtained. There is always a fluctuation in the relationship curves between the strain energy and the actuating displacement. It can be forecast that the shaping can be achieved if there is an energy fluctuation. The energy level also increases with the loading angles, and the actuating displacement corresponding to the energy fluctuation increases with the loading angles. The energy fluctuation also can reveal the minimum actuating displacement and minimum actuating force levels that have similar trends as the fluctuation. We can find that the model cannot return from the folding stable state to the initial flatter state rely solely on the compression of the central square facet. However, the recovery step is also important for reconfiguration and reuse. So we also discussed the recovery method of the Kirigami-inspired model. These two intersections are subject to vertical downward displacement V relative to the other two intersections. And we can obtain the relationship between the strain energy and the vertical actuating displacement and the relationship between the rotational angle and the vertical displacement during the recovery process. The strain energy increases with the vertical actuating displacement first to a peak in state R2, and then it falls significantly to a bottom in state R3. From state R2 to state R3, the vertical actuating displacement increases slightly, while the model configuration changes noticeably. After removing the external loads from state R3 to R4, the vertical displacement and rotational displacement of the central square facet are basically unchanged and remain around there. We want to achieve the reconfigurable surface connected by the Kirigami-inspired element with short creases. We discussed two different connection models, A and B, and the difference is whether there is a continuous creases at the corner. For the surface with model A, there is no shaping during the process. When the surface is designed with model B, each element has a similar motion trends as that of the isolated elements. At last, the stable folding states of the two elements are both obtained. So the model B is selected to the connection width of the basic element of the reconfigurable surface. After that, we performed a similar analysis on the one-dimensional arrays with 4 Kirigami elements. They all can arrive at the design-folded stable configuration. Moreover, we can find that the shaping process is asymmetric. On the whole, the middle elements are formed first, and the elements on both sides are formed later. The results are similar to that of the two-dimensional arrays with 8 Kirigami elements. The stable forming of the middle elements precedes that of the two side elements. Let me conclude my talking by highlighting what we did and what we learned. First, we have discussed the bistable behavior and self-locking phenomena of the Kirigami-inspired model. Then, we proposed the shaping and recovery method of the Kirigami-inspired elements. We also performed the parametric analysis to investigate the effect of the actuating position. Last, the connection detail of the surface composed of the many elements are compared and determined. Besides, one-dimensional areas with 4 Kirigami elements and two-dimensional areas with 8 Kirigami elements are used to verify the shaping method can be extended to 2D surface. Based on the pre-designed Kirigami pattern, the proposed shaping and recovery method can be extended in the future, including the influence of the geometry, actuating mode with line loss, the shaping and recovery of the many elements on one surface with different connection models, design, shaping, and reconfiguration of the complex 3D surface based on a basic 2D surface will be investigated deeply. With this, I would like to thank you again for your attention.